All right, today we're going to go through chapter 19, which is electrochemistry. It starts off doing oxidation reduction. So we're going to do our oxidation reduction again. And of course, the PowerPoints do it one way, I do it another. It doesn't make any difference if you do it whatever way you do it. If you get the correct answer, you should be doing it right, but you have to get the correct answer every time. All right, so we're going to balance oxidation reduction, half reactions, and acid and base solution. Then we add them up with the electrons canceling. And then we're going to get into voltaic cells. All right, so voltaic cell employs a spontaneous. Delta G is negative, spontaneous. All right, so we know when it says spontaneous, we know delta G is negative. Oxidation reduction reaction as a source of energy. It separates the reaction into two half reactions. We're going to have an oxidation. We're going to have a reduction. The electrons, we're going to actually draw a voltaic cell. Electrons move from the oxidation through the external circuit to the reduction half reaction. All right, so we're going to all that stuff we know. All right, so we're going to balance oxidation reduction. All right, so we'll go through the way the book does it a little bit. All right, so just to see the difference in the way I do it. First, you identify what's being oxidized, what's being reduced. That's giving your oxidation numbers. That's the first thing that you do. You got to get your oxidation numbers. All right, so once you see that one increased in oxidation number, that's the oxidation half reaction. One decreased in oxidation number, that's the reduction half reaction, and you put them into two reactions. And then the problem will say acid or the problem will say base. So, of course, in acid, we're going to use H plus to balance the charge. In base, we're going to use OH minus to balance the charge. All right, so I'm going to go back and do this problem the way I want to do this problem. All right, so we have Fe plus 2 plus MnO4 minus, and of course, you can do it the way that the book does it. You get Fe plus 3, and you get Mn plus 2. So I'm going to go through the steps the way I think it should be done, and then they'll do it their way. And you can see, I will tell you why I prefer my way. All right, so I see, first thing I do is I give my oxidation numbers, plus 2 for your iron here. Now remember, oxygen is always minus 2, but you have 4 of them. That means you have minus 8. The overall charge is negative. And so this is a plus 7. A 7 minus an 8 is a negative 1. So your Mn here is a plus 7. All right, your Fe here is plus 3. Your Mn here is plus 2. All right, so if you are an ion, monatomic ion, your oxidation number is the same as your charge. When you are with oxygens, oxygens are minus 2 unless it is a peroxide, where it's minus 1. All right, so this is 4 minus 2s. And so then you can get your oxidation from that. And these two are just monatomic ions. So oxygen, remember, is going to be negative 2 in compounds, and hydrogen is going to be plus 1 in compounds. And the entire column of the hydrogen column, every one of those, lithium, sodium, potassium, all of those are plus 1. The second row, the second column, is always a plus 2. So that's with your beryllium, your magnesium, your calcium. Those are always plus 2. So group 1, always plus 1. That includes hydrogen. Group 2 is always plus 2. Now the other ones you have to determine by using the rule where oxygen is minus 2 unless it's a peroxide, where it's minus 1, and hydrogen in compounds is always plus 1 unless it is a metal hydride. So if you had NaH, there's no exceptions to in compound sodium is plus 1. So in this case, your hydrogen has a special case where if there's a metal first, then the H is a -1. All right, so you assign your oxidation numbers. Then you see that you increased an oxidation number. From here to here, you went from a +2 to a +3. That is our oxidation. We increased the oxidation number. And so you have Fe plus 2 going to Fe plus 3, and this is your oxidation half reaction. You see that your Mn went from a +7 down to a +2. That is your reduction half reaction. So you have your MnO4 minus going to Mn plus 2. All right, so then you're going to balance everything that's not hydrogen and oxygen. All right, so you have to balance the atom that's changing the oxidation number. All right, so don't worry about any oxygens. Just make sure that you have the same number of irons on both sides, and we do. It's 1. Make sure you have the same number of Mns on both sides. So there's 1 manganese on each side. Do not skip that step. Check to make sure that everything is balanced except for your hydrogens and your oxygens. So that's going to be the things that are changing the oxidation state. All right, so this is your reduction half reaction. All right, so now this is not what the book does, and I don't agree with it. The electrons are what balances your oxidation numbers. All right, so you are going to balance your oxidation numbers with electrons. They never do that in the book, and I don't know why, because that is a very important part of your oxidation reduction. It is all about the electrons that are being transferred from one to the other. All right, and so we see that a iron plus 2 going to an iron plus 3 needs 1 electron for a plus 3 iron to go to a plus 2 iron. And of course, the reason why they don't do it this way is because people get confused. But the way they do it, people get confused too. But I like balancing the oxidation numbers with electrons. All right, and so here I know that to go from a plus 2 to a plus 3, I have to lose 1 electron. All right, so electron is a negative charge. If an iron plus 2 loses a negative charge, it then has another positive charge. When I see my Mn going from a plus 7 to a plus 2, I know that I have to add 5 electrons to that, because plus 7 minus 5 gives us a plus 2. What I'm going to put up here is this is per iron, and this is per Mn. For every iron, I have to lose 1 electron. For every Mn, I have to gain 5 electrons to go from a plus 7 to a plus 2. All right, and so this is where people will have their plus 3 electrons over here because they're balancing the charge. Electrons do not balance charge, and that's why I would not do the book, because they balance their charge with electrons. That is not the way it works. The way it works is you balance your oxidation numbers with electrons. And so this needs 5 electrons. So your plus 7 going to plus 2, you need the 5 electrons. All right, so now after you've balanced your oxidation numbers, that's when you have your balance of charge. So you balance oxidation numbers. I balance that. First thing that I'm balancing. All right. After I have all of my oxidation numbers and I broke it into half reactions, what are my things that I broke it into my oxidation and reduction? First thing I do is I balance my oxidation numbers with electrons. Second, I balance the charge. Now, acid means H+. So balance the charge. In acid, I'm going to balance it with H+. If it said base, I'm going to balance it with OH-. The way the book does it, they always do an H+, and then if it's base, they add whatever H pluses they have. They add that many OH minuses. They make water. They subtract the water. I feel like that is way too many steps that are not necessary. Again, if you like to do it that way, that is fine. All right, so I see my charge. Remember, your charge is the overall charge now. Before, we weren't looking at the overall charge. We were looking at the oxidation numbers. For the first reaction, you could do it all wrong and still get it right because the charge and the oxidation numbers are all the same. So you got plus 2, you got plus 3, you got minus 1, you got plus 2 is equal to plus 2. So in this one, it's already equal. You got a plus 2 on this side, that's equal to a plus 2 on the other side. All right, here for 1 MnO4 minus, you got -1. For 5 electrons, you got -5. For 1 Mn plus 2, you got +2. A -6 does not equal a +2. All right, and so you have to add enough hydrogens. If I added 6 of them, I would be at 0. I need to add 8 of them to get to +2. All right, so now I have a +8. And then -1 and a -5. So now I have a +2 on this side, which is equal to a +2. The number doesn't make any difference. It just has to be the same number on both sides. This one happened to be both +2s for both the oxidation half reaction and the reduction half reaction. All right, so then the third thing we're going to balance is our hydrogens and oxygens. And we're going to use water. All right, so all ions are aqueous. So for acid, H+, it's aqueous. That means we have water. OH-, that's a negative charge. That's aqueous. We know we have water. And so we are going to balance our hydrogens and oxygens with water. There are no hydrogens and oxygens for oxidation half reaction. It is a balanced reaction. All right, so here we have 8 hydrogens, and over here we have 0 hydrogens. And so we would need 4 H2O to give us 8 hydrogens. And then we check our oxygens. 4 waters, of course, is 4 O's. MnO4, that's 4 O's. All right, and so now we have our balanced electrons using our oxidation numbers, our charge using H+ for acid or OH- for base, and then we balance our hydrogens and oxygens with water. Then finally, your electrons gained must equal electrons lost. All right, and so what we have to do is multiply the first one through by 5. All right, and so that will give us 5 electrons lost and 5 electrons gained. So you multiply it through 5 Fe plus 2s, 5 Fe plus 3s, 5 electrons. And so your 5 electrons are going to be subtracted from both sides. So your overall is 8 H plus. That is, we're going to react with 5 Fe plus 2s. That's going to react with MnO4 minus. That is going to produce 5 Fe plus 3s and Mn plus 2 and 4 waters. You may want to check the charge when you're finished to make sure that you didn't forget to bring down any coefficients. On this side, you got a +8. Then you got 5 plus 2s. This is +8. You got 5 plus 2s. That's +10. You got an MnO4 minus. So you got an 8 plus a 10, which is 18, minus a 1. This is a +17 on this side. All right, and it better be +17 on the other side. We got 5 plus 3s. That's +15. We got 1 plus 2, +2. We got 4 neutrals. And so you see that we have both a 17 plus on the reactant side and a 17 plus on the product side. All right. Now, the oxidation half reaction, you're going to be asked to label your reactants, or not even, it's not going to say reactants, but it's going to say label your oxidizing agent and your reducing agent. All right, from your oxidation half reaction, the reactant, and it's always a reactant that's going to be your oxidizing agent or reducing agent. The reactant of your oxidation half reaction is always your reducing agent. So this is your reducing agent. Why is it called the reducing agent? Because if we had MnO4 minus and we wanted it to be reduced to Mn plus 2, we just add iron plus 2, a reducing agent. MnO4 is the oxidation, it's the oxidizing agent. It is the reactant of the reduction half reaction. And so this is your oxidizing agent. Again, why is it called an oxidizing agent? If I had iron plus 2 and I wanted to oxidize it to iron plus 3, I would grab some MnO4 minus, the oxidizing agent. It would oxidize iron plus 2 to iron plus 3. All right, and so you will have a oxidation reduction reaction to balance. I don't grade the steps, I grade the work. As long as you're doing all the work, getting the final answer, everything is great. All right, again, the book does it differently. All right, so And this is a typo, MN04. Well, I guess they're just looking at the MN. All right, so they got their oxidation numbers. They determine the oxidation numbers. All right, and so they say that's our oxidation, +2 to +3, and then a +7 to +2, that's a reduction. Then they break it into the two half reactions. They don't show all the stuff they're doing. All right, so here's the rules that they go with. I would put in my differences. First, they assign oxidation numbers. Yes, that is what you have to do. You have to know what's being oxidized, what's being reduced. You break it into two half reactions. All right, so yep, so that's the same steps that I do. 1 and 2 are the same. All right, so then is where it is different for me. They use a different method that gives you the balanced reaction, but is not really doing it the way that the reaction is intended to be doing. They're balancing the charge with electrons. No, you balance the oxidation numbers with electrons. All right, so again, fine, this gives you the right answer, but it's not doing it the way that I would do it. All right, so I in number 3, balance electrons, balance the oxidation numbers using electrons. All right, so balance your oxidation numbers using electrons. Then you balance charge, and they use H plus every time, and if it's in base, then you add whatever it's. I'll show you how they do it. Not in this method. You balance the charge. If it's acid, you balance it using H plus. If it's base, you balance it using OH minus. And then finally, you balance your charge. Balance charge. You balance your hydrogens and oxygens with water. All right, electrons, overall charge, and then H's and O's. They balance the H's and O's first. In my opinion, should be done last. And then every time they balance the hydrogens with H plus, whether it's acid or base. And then if it's base, then they put in as many OH minuses as H plus. It seems not the way to do it, but fine. All right, so once you have your balanced half reactions, then everything should be the same. All right, so 4 is going to be the same either way. You multiply each half reaction by a factor so that the number of electrons gained is equal to the number of electrons lost, and then you add up your two half reactions and be sure that your electrons gained and lost are the same so that they do not show up in the overall reaction. They always cancel. Then simplify the overall reaction by canceling species that occur on both sides. Okay, I do that as part of the add up the two half reactions. I don't put 5 electrons and 5 electrons and then cancel them. I cancel the 5 electrons before I add them up. If I had 2 waters and I had 5 waters, I'd cancel 2 waters on both sides and have 3 waters at the end. But they're being very clear, if you have water on both sides, that is not the correct answer. All right, so water can only be on one side. H plus can only be on one side. OH minus can only be on one side. You would have to subtract that number that is the lowest number so that it is gone on one side and still on the other. All right. Then another one is your coefficients have to be the smallest whole number. So if you notice all of your coefficients are even, then you know you need to you have to divide through by 2 or multiply through by 1/2. You want the smallest whole number coefficients. And then you just check. By checking to see if it's balanced, I usually do the charge. Usually if your charge works out, you have brought everything down with the correct coefficients. All right, so there's that half reaction. All right, so I can show, well, I don't think they do a base one. Oh, so see how they bring down the 5 electrons and the 5 electrons and then they cancel it. That is not the way I do it. I cancel them up here. 5 electrons, I multiply through by 5. and I cancel that 5 electrons with that 5 electrons, and I go to the answer. I don't put in the 5 electrons and then cancel them. But again, doesn't matter. The final answer and showing your work, that is what's important. All right. Zinc metal reacts with nitric acid to produce a number of products depending on how dilute the acid is. Concentrated solution, zinc reduces nitrate ion to ammonium ion, and zinc is oxidized to zinc plus 2. Write the net ionic equation for this reaction. All right, so we have a zinc plus 2 going to, we have a zinc going to a zinc plus 2. So we have zinc metal, 0, going to zinc plus 2. So this is our oxidation half reaction. A 0 going to a plus 2. All right, so then we have HNO3. And they say that this is going to go to the ammonium ion. That is NH4 plus. Now, getting the oxidation numbers here are quite interesting. So H is always plus 1, O is always minus 2, unless you are a peroxide. So this is a minus 6, this is a plus 1, and so you see that this is a neutral molecule. Your nitrogen is a plus 5. All right, nitrogen is not a metal. The only time H is minus 1 is if it has a metal first. Nitrogen is a non-metal, so these H's are all plus. So this is plus 1 each, so this is a plus 4. Overall, it's a plus. So this nitrogen on this side has to be a negative 3. So a 4 minus 3 is 1. All right, so your oxidation half reaction is very simple. We had to lose 2 electrons, so to balance that, we put in 2 electrons, and then the charge, no charge, no charge, hydrogens, none, none, oxygens, none, none. Everything is balanced. That half reaction is very simple. Now, this half reaction is not so simple. All right, so the most common error when you see a plus 5 to a minus 3 is to say that it had to gain 2 electrons. Well, no. 2 electrons is a plus 3. Plus 3 does not equal negative 3. All right, so this one needs 8 electrons. And so we need to gain 8 electrons per nitrogen. And we do just have 1 nitrogen on both sides. And so we have 8 electrons here. All right, so that was balancing the oxidation numbers. All right, so then with electrons. All right, so now we're going to balance charge. All right, and so of course, if we're in nitric acid, we are in acid. All right, and so we're going to use H plus to balance our charge. So on the left, HNO3 is neutral, and we have 8 electrons. So we have minus 8 on this side. On the right side, we have 1 NH4 plus. That is a plus 1. All right, and so we have to add 9 H pluses. 9 H pluses to this side. So now we have a plus 9, we have a minus 8, and that is equal to a plus 1. And so we have plus 1 is equal to plus 1. So we balance the charge with H plus. All right, first oxidation numbers, then charge, and now your H's and O's with water. All right, and so on the left, we have 3 oxygens on the left, and so if we write in 3 H2Os to get our 3 oxygens, let's check our hydrogens. We have 9 plus 1, we have 10 hydrogens on the left. We have 4 plus 6, we have 10 hydrogens on the right. And so that is a balanced half reaction. So that's the oxidation half reaction. Here's the reduction half reaction. So zinc is your reducing agent because it reduced the HNO3 to NH4 plus. The HNO3 is your oxidizing agent because it oxidized the zinc 0 metal to the zinc plus 2 ion. Now, before you can add these up, you got to make sure your electrons gained equal your electrons lost. And so you see we have to multiply the zinc half reaction through by 4. And so we'll have 4 ZNs. We'll have 4 ZN plus 2s. And we will have 8 electrons. So now the electrons that are 8 here cancel with the electrons that are 8 there. And then we bring down our 4 ZN plus 9H plus HNO3 yields ZN plus 2, 4 of them. We have an NH4 plus, and we have 3 H2Os. All right, and you'll want to check the charge. All right, so we have 4 zeros, we have 9 pluses, that's plus 9, and we have neutral. So 9 is what we have on the left. Here we have 4 plus 2s, that's plus 8. Here we have an NH4 plus, that's plus 1, and we have 3 neutral waters. And so we see that a plus 9 on the left and a plus 9 on the right. So that is our balanced oxidation reduction reaction. All right, so you got to follow the steps. Again, this is my order. This is the order that I believe everyone should do it in. Another order will get you the right answer. Interesting that they, which is fine. This is the same thing. They wanted the net ionic. Okay, so they were clear that they wanted the net ionic. All right, of course, in the net ionic, HNO3, that is a strong acid. So they asked for the net ionic equation. All right, so in the net ionic, HNO3 is a strong acid, and so that breaks up into H plus and NO3 minus. So it should have been written with 10 for your H plus. All right, and then it should have been written as an NO3 minus for your HNO3. All right, so the net ionic, if you have, of course, a strong acid, it would break up into H plus and NO3 minus. If it was a weak acid, then you would leave it the way it was before. All right. So here's their explanation of if you're doing it the way the book does it. If you have one that's in base, all right, the number of H plus ions that you'd put in, you would add that same number of OH minus to both sides, and your H plus and your OH minus react to form H2O, and then you cancel the waters on both sides. All right, so you can do it that way. I do not do it that way. All right, so when we are balancing this, again, we already did MnO4 minus, oxygen's minus 2. There's 4 of them. That's minus 8. And so again, your Mn is plus 7 in MnO4 minus. Oxygen minus 2, that's minus 6. In order to get a minus 2, your S, Mn here, of course, is plus 7. S here is a plus 4, or minus 6 is minus 2. All right, you got 2 oxygens on your MnO2, so that's minus 4. It's neutral, so the Mn on this side is plus 4. And then your SO4 minus 2, 4 minus 2s, that's minus 8. And S has to be a plus 6 in order to get a negative 2 overall charge. And so you see with your Mn going from a plus 7 to a plus 4, this is going to be the reduction half reaction. All right, and we are going to gain 3 electrons per Mn to go from a plus 7 down to a plus 4. All right, your SO3 minus 2, that sulfur has an oxidation of plus 4. SO4 minus 2 has a plus 6. All right, and so we are losing 2 electrons per sulfur. All right, and so there's 1 Mn on both sides, there's 1 sulfur on both sides, because that is what you do immediately after you break it into 2 half reactions. So you have your MnO4 minus, that goes to MnO2. that is your reduction half reaction, because you're going from a +7 oxidation down to a +4. Your SO3 minus 2 goes to SO4 minus 2. That is your oxidation half reaction, going from a sulfur that's +4 to a sulfur that's +6. So that is your oxidation half reaction. All right, and so we balance the electrons up on the top. So we had a +7 going to a +4. So we knew that we had to add 3 electrons. We have our +4 going to our +6. That means we had to give off a product, 2 electrons. So I like to put the electrons up here when I'm determining my oxidation numbers, and then I bring them down into my half reactions. All right, so now we have our balanced oxidation numbers with our electrons. So now we balance the charge. So again, balance oxidation numbers with electrons, done. Then we are going to balance the charge. All right, we are in base. All right, so basic solution. Basic solution, usually it's written out here as well, in base, we're balancing it. That means we have to use OH minus to balance the charge. All right, and so we see we have on the left side here, we have 3 electrons, that's 3 negative. All right, so -3, we got 1 MnO4 minus, that's another negative, so that's -4. On this side, we have a -4. On the other side, we have no charge. All right, and -4 does not equal 0. We are adding OH minuses, so we need 4 OH minuses in order to get our -4. So now we have -4 is equal to -4. For the oxidation half reaction, all right, we have a overall charge on the left of -2, and on the right we have -2 and the 2 electrons, another -2. So a total of -4 on the right side. In order to get our charge to be the same on both sides, we add 2 OH minuses. And so that's another -2. So now we have -4 is equal to -4. So that's how you balance the charge. All right, and now we are going to balance the hydrogens and oxygens with water. All right, if we look at the oxygens, we have 4 on the left, and on the right, we have 4 here, plus 2 more here. So we have 6. So we need to add 2 waters. All right, so 2 waters gives us 6 oxygens on the left and 6 oxygens on the right. We check our hydrogens. 2 waters is 4 hydrogens. 4 OH minuses, that is also 4 hydrogens. We have our balanced reduction half reaction. All right, oxygens on the left. We have 1 here, we have 3 here. That is 4. We have 4. The oxygens are balanced. Oh, sorry, there's 2 here and 3 here. That's 5. They are not balanced. This one is 4. So you have 2 OH minuses. That's 2. SO3, that's 3 more. That's 5. Over here, we only have 4. So we need 1 H2O on this side to give us 5 oxygens on both sides. And then we see we have 2 hydrogens on the left, and we have 2 OH minuses, 2 hydrogens on the right. So now we have a balanced oxidation half reaction. So now we're going to add them up. But before we can add them up, we have to have the same number of electrons on both sides. Right now, we have 3 electrons gained, and we have 2 electrons lost. And so the least common factor between your 3 and your 2 is 6. Normally it works. You would multiply this reaction through by 2 and this one by 3. That works, except sometimes that's not always the least common factor. And then you would have to reduce it down if it's not. But here, we're going to multiply this all through by 2 so that we have 6 electrons gained. And then we're going to multiply this whole reaction through by 3 in order to also get 6 electrons lost. All right, and so now we have our 6 electrons, and our 6 electrons, they are going to be gone. Now when we multiply this through, so now we have a 2 for our MnO4 minus. We have our 2 for our MnO2. And now instead of 4, we have 8 OH minuses. When we multiply this through by 3, not 2 OH minuses, but 6 OH minuses, a 3 in front of the SO3 minus 2, a 3 in front of the SO4 minus 2, and then our electrons were already canceled, and then a 3 in front of our H2O. So now we're going to bring it down. All right, the way I forgot to multiply the water. Okay, so this is a 4. When you multiply this through by 2, this is now 4 H2O. Now when you add them up, you cancel out the electrons. All right, you got 8 OH minuses on this side, you got 6 on this side. This 6 is gone, and this is down to 2. You got 3 waters on this side, you got 4 waters on this side. This side, the water is gone, and now we're down to just 1 H2O. All right, and so you bring it down. You have your 2 MnO4 minus. You've got your 3 SO3 minus 2. You've got your 1 water. All right, now you have your 2 MnO2s. You've got your 3 SO4 minus 2s. All right, you have now only 2 OH minuses left on this side. And of course, your waters have been subtracted 3 from both sides, and so it is gone on the right. So when you're done, to make sure you brought everything down with the correct coefficients, you should check the charge. You've got a minus 2 here. You've got 3 minus 2s here. So that's minus 6, and that is neutral. So on this side, you got a minus 8 total. Hopefully that's equal to 2 zeros and 3 minus 2s, that's minus 6, and 2 minus 1s. And so that is equal to negative 8. So minus 8 charge on both sides. And so there is your balanced oxidation reduction half reaction. All right, we see that the MnO4, that was part of our reduction half reaction. So again, this is your oxidizing agent. And your SO3 minus 2 is your oxidation half reaction. So this is your reducing agent. And the agents are always the reactant. Do not say that Mn is an oxidizing agent. No, Mn is not an oxidizing agent. It has to be the reactant. Mn is not even a reactant or a product. All right, that is in one of our reactants. The oxidizing agent is MnO4 minus. It has to be the whole entire reactant, not just the atom that's changing oxidation number. It is the entire reactant. Same with your reducing agent. It is not S. It is SO3 minus 2 is your reducing agent. All right, so they will go through the process, and when they're done, they get this as their answer. All right, but the problem says that it is in base, and so what they do is they add 2 OH minuses to both sides. And then the 2 OH minuses with the 2H plus add up to 2 H2Os, and then they subtract an H2O from both sides, and that's how they get their balanced reaction. So they will show that you add 2 OHs to both sides, that's 2 waters, and then they subtract the water from both sides, and then they have the same exact answer that we had. Again, if you want to do it that way, that is fine. All right, so that was oxidation reduction. Now we're going to do our half reactions in an electrochemical cell. All right, and so we're going to have a system that has electrodes that are metals that dip into an electrolyte, a aqueous solution of a usually a metal, but it could be H plus as well. All right, and it's either going to use or generate an electric current. So of course, if it generates an electric current, it is going to be spontaneous, and delta G is negative. If it's going to require an electric current, then it's going to be non-spontaneous, where your delta G is positive. When it is a spontaneous reaction in your electrochemical cell, it is called a voltaic cell or a galvanic cell. So as soon as you see the term voltaic cell or galvanic cell, you know that this is spontaneous. You know that your delta G is a negative value. They're telling you by saying that this is a voltaic cell or a galvanic cell that the delta G is negative. It is spontaneous. If it says it's an electrolytic cell, they're now telling you that it is not a spontaneous reaction. All right, and so now this is a non-spontaneous reaction that would require some external energy to make that reaction go. And so here we know that delta G is going to be positive. All right, so that is what you get from just a word in the problem. In this voltaic cell, in this galvanic cell, okay, we know it's spontaneous. And this electrolytic cell, we know it's non-spontaneous. If it's spontaneous, your delta G is negative. If it's not spontaneous, your delta G is positive. All right, so physically, a voltaic cell consists of two half cells that are electrically connected. All right, so a half cell is a half reaction. You're going to have an oxidation half reaction. You're going to have a reduction half reaction. All right, and we're also going to have a salt bridge to connect them so that the electrons can flow. So electrical connections allow the flow of electrons, and your salt bridge will allow the ions to flow. So you're going to have your salt bridge in order to balance out your charge, so you're not getting a high positive charge on one side and a high negative charge on the other side. We are balancing out our charge. All right, so here is an example of they don't say which kind it is. I think this is a galvanic cell. All right, where you have your zinc on one side and you have your copper on the other side. All right, and so your electrodes are these metals that you're going to connect to. So that is a zinc metal. All right, and this is your copper metal. And so in solution for this one, we have our zinc plus 2 ions. And so this solution contains zinc plus 2. And in this solution, it contains copper plus 2. So this is your copper plus 2. And now they're blowing it up and telling you what's happening. So what's happening here is our zinc metal, our electrode here, the zinc electrode metal, this zinc is being oxidized to zinc plus 2. And so you're losing mass of your metal because the metal is oxidizing from a zinc to a zinc plus 2. So your zinc metal is going to a zinc plus 2. So that is your oxidation half reaction. Now your copper is going from a copper plus 2 to a copper solid. So a copper plus 2 is going to a copper solid. All right, and so that is your 2 reducing down to 0. This is your reduction half reaction. All right, and so what's happening here is that your zinc plus 2, which is your solution, is now forming your copper plus 2, this blue solution, is now forming copper metal. And so these atoms are coming in, or these ions are coming in and forming an atom. All right, and so you have your zinc plus your copper plus 2, it is going to make copper metal. And so if you could blow this up, you see that this metal is getting bigger. So this is getting smaller amount of metal. And this is getting larger. This is getting larger. All right, so if you weigh the electrode before and after, your zinc electrode is going to lose mass. Your copper electrode is going to gain mass because the copper is depositing onto your copper surface. All right, and so that is where the reduction is occurring. The oxidation is the zinc metal is being oxidized to the plus 2 ion, so it's going into solution. And then you have your salt bridge here to make sure that you're not going to be generating too much negative charge or too much positive charge. And that again, of course, is called the salt bridge. So it is a tube of electrolyte. So KNO3. So any salt would work here. KNO3 is a very common one, but it has to be some salt that is in a gel that is connected between the two half cells of a voltaic cell. It allows the flow of ions, but prevents the mixing of the different solutions. And so you're not mixing your copper +2 and your zinc +2, but it will allow flow of these ions. The K plus goes to one side, the NO3 minus goes to the other side to make sure that you have a neutral solution so that you're not building up a high electric charge. All right, so in the salt bridge, the cations move toward the cathode, the anions move toward the anode. All right, so we're going to talk about cathode and anode. All right, so the anions move to the anode. The ions that are at the anode are called anions. The ions that are at the cathode are called cations. All right, so if your ion is hanging out at the cathode, it's a cation. If your ion is hanging out at the anode, it's an anion. So cations are positive. All right, your anions are negative. And so the positive cations are hanging out at the cathode because the cathode is negative. All right, and that attracts the positive ions. And so the ions that are at the cathode are called cations. The anode is positive, and that attracts all these negative ions. And so these negative ions that are at the anode are called anions. All right, so the electrode at which the oxidation takes place is called the anode, and that will always be on the left. All right, so when you have your drawing your cell, the anode is always on the left. All right, and then the cathode, that is where your reduction takes place, and that's always going to be on the right when you draw a cell. All right, and so I always remember red cat. All right, so if you forget what is happening at the cathode, reduction at the cathode. So it's easy to remember if you just remember red cat, reduction's at the cathode. All right. So the net reaction that occurs in a voltaic cell is called the cell reaction. All right, and of course, if it is a voltaic cell, that means it's spontaneous. That means delta G is negative. All right, so the electrons are going to flow through the external circuit, usually connected by some voltmeter to measure the voltage from your anode to your cathode. All right, so, or you can hook up a flash or some sort of light bulb and see the light bulb light up. But many times here you hook up a voltmeter. Or, of course, you can just put in a light bulb and the light bulb will light up. All right, and so here is when you're drawing a cell, this is what it would look like. Now, this is your oxidation that occurs at the anode. The anode is always on the left. This is your reduction, +2 going to +2 going to 0. That is reduction, and that's the red cat. So the reduction is at the cathode. All right. The salt that they used was KCl. So we put a KCl in here. All right. And so to neutralize the charge, remember that in the anode here, the zinc is breaking off of this metal and oxidizing into zinc +2. So you're building up a huge positive charge here. And so the salt bridge sends all the Cl minuses down in here. All right, for every one Zn +2 that's formed, 2 Cl minuses will come in there to neutralize that charge. Over here, we have a +2 copper going to the metal. So +2 going to 0. All right, and so what we're having here, and if you want to have, you don't have just zinc plus 2, there has to be the counter ion that is soluble. So it could be, usually it's, say, a zinc nitrate or a zinc chloride, whatever. All right, and so same with the copper sulfate. So there's some other negative ion in here. So if you put it in as CuSO4 and that dissolves into Cu plus 2 and SO4 minus 2, when the Cu plus 2 is going to form copper metal, you still have an SO4 minus 2. So you're going to build up a lot of negative charge. And that's why every time one copper plus 2 is reduced into copper metal, you're going to have 2 K pluses that are going to come into this solution through the salt bridge to neutralize the SO4 minus 2 or whatever counter ion was used in this dissolving of the copper. All right, and so again, your anode, that is where your oxidation occurs. That is always the first on the left side. That's what you draw on the left side. And then the cathode is always what you draw on the right side. And you need to know that your electrons always flow from anode to cathode, alphabetical order, A to C. All right, so our electrons, they have the arrows. The electrons are flowing from your anode to your cathode through this external circuit, which is normally a voltmeter, but could also just be a light bulb. It could be very common to have a digital clock here. It can run a clock. Anything you set up here that needs a small voltage to run, you could set it up there. Normally, we're just set up a voltmeter, read the voltage. All right, and so that is how you will have to draw one of these on the test. Don't have you draw the light bulb. You just put in a voltmeter, and then we're going to do that next, calculate the EMF, the voltage of this cell, and then that would be part of the question too. What should the voltmeter read if you set this all up correctly? All right, so you always have a metal electrode on both sides. The one that is the oxidation, always on the left. One that's the reduction, always on the right. All right, so here's a picture of connecting it to a voltmeter. All right, and so the blue solution is your copper. All right, and then the clear solution, that's your zinc. So here's your copper plus 2 solution. Here's your zinc plus 2 solution. This is your zinc solid metal electrode. Here is your copper solid metal electrode. And this U-shaped is your salt bridge. All right, so then you hook it up to your voltmeter. And if you have a zinc copper electrode, it will read, if you have 1 molar solutions, it will read 1.10 volts. And so here is 1.10 volts. You get a voltage from this cell. All right, so a voltaic cell. All right, so we now know it's spontaneous. So as soon as you see this, you know it's spontaneous. It's going to generate electric current. Delta G is negative. All right, and so we're going to have a half cell in which the cadmium rod dips into a solution of cadmium nitrate. All right, so we do the net ionic. So this is cadmium solid, and this is cadmium plus 2. And another half cell in which the silver, Ag solid, is dipped into a solution of silver nitrate. So you got Ag solid and you've got Ag plus. All nitrates are soluble. So this is Ag plus. All nitrates are soluble. This is Cd plus 2. All right, and then they're connected by a salt bridge. All right, so the silver ion is reduced during the operation of the voltaic cell. All right, so again, if you do the forward reaction and it's voltaic and you get a spontaneous reaction, the reverse reaction is going to give you a positive delta G, which means it is going to be an electrolytic cell. All right, so one way this goes, you get a voltaic cell. The other way would be an electrolytic cell. And so when we know that it is a voltaic cell, we must set it up so that it is the spontaneous reaction. So the silver ion is reduced during the operation of a voltaic cell. So they're telling us that we are going to reduce the silver ion for this. So we know that Ag plus is going to go to Ag. They're telling us that in the wording here. It is reduced. The silver ion is reduced. This is the reduction half reaction. So if they're telling us that, then the other side has to be the oxidation reaction. All right, and so now your cadmium going to cadmium plus 2. That is your oxidation half reaction. Because in a cell, you have an oxidation occurring and you have a reduction occurring. All right, and so remember the anode. So we can balance these. These are very simple. So the cadmium up here, you just need your 2 electrons, and it's balanced. For your silver, we need 1 electron, and it's balanced. However, when we add them up, we're going to have to multiply this through by 2, because if we have 2 electrons lost, we have to have 2 electrons gained when we add these up. All right, so we're going to label the anode. Remember, red cat. So the cathode is where the reduction occurs. The anode is where the oxidation occurs. All right, and so we label the anode and the cathode. The anode is the oxidation. The cathode is the reduction. All right, and electron flow is always anode to cathode. And so when we draw it, we're going to have to draw our cadmium on the left, because the left side is always the anode where the oxidation reaction is going on. We're going to have to write the silver on the right, because that is the reduction half reaction. That's the cathode. Anode first, cathode second. And then we have to show the electrons flowing from our external circuit that's hooked to a voltmeter or a light bulb or something else that goes from anode to cathode. All right, and then make sure you put in your salt bridge. All right, so here is, all right, so they told us that the silver was the reduction. And so if that's the reduction, then of course cadmium has to be the oxidation. And since the electrons loss was 2, that's why we multiplied this through by 2. So we had 2 electrons gained and 2 electrons lost. So here is the picture. Again, the anode, that's the oxidation. So here's your anode. Here's your cathode. All right, so again, you then have a cadmium metal. You connect your electrode, you connect your voltmeter up to that. They hooked up a light bulb to it. I'm going to hook up a voltmeter to it. All right, and then of course on the other side you got silver. So you've got a silver. I don't know why they're drawing silver the color of copper, but whatever. Silver is actually silver, not copper. All right, whatever. You can draw it any color you want as long as you label it. It's silver. And so you then have your connection to your silver cathode. So your electrodes are metals that you're hooking your alligator clips to from your voltmeter. All right, and then you always have to have a salt bridge. Right, and so if we're using KCl like we did last time, we know that on your oxidation side, cadmium is going to cadmium plus 2. All right, and so we're building up a bunch of plus charge, and so we have to neutralize that. So the Cl minuses are going to be going this way. Our Ag pluses for our AgNO3, this is NO3 minus in here. As the Ag plus goes to Ag solid, we're going to build up a bunch of excess NO3 minus ions. And that's why the K plus is going to be going in here to neutralize the charge in that in the cathode. All right, again, electrons always flow the external circuit, anode to cathode. Electrons always flow from anode to cathode. All right, again, you will be drawing this picture. All right, anode's always on the left, cathode's always on the right. Anode is always oxidation, cathode is always reduction. All right, so now we're going to have a shorthand. All right, so a shorthand for a voltaic cell or any cell. And the way that we do this notation is always the anode comes first, then you have your salt bridge, and then you have your cathode. It must start with a metal. It must end with a metal. All right. Anytime you have a single line, so a double line here, that is your salt bridge. So the double line, that is your salt bridge. Anytime you have a single line, that is a phase change. All right, so here we're going from an aqueous liquid phase to a copper solid phase. And so that's why it has the 1 slash. My slashes are usually slanted, not straight up and down. It's fine. I don't care if they're straight up and down or slanted. I always use slanted lines. All right, if you have a concentration for your ions, it would go right after this. So in this case, if it's not given, all concentrations are 1 molar. All right, so if the concentration is 1 molar, then you don't have to write the 1 molar. I would get in the habit of always writing the concentration because it is going to be required to put the concentration when it is not 1 molar. All right, so you would label the zinc plus 2, then you would label your concentration of your zinc plus 2. Putting in the solid here, putting in the aqueous here, not required. If I have zinc, it's zinc solid. If I have zinc plus 2, all ions are aqueous. I do not need to put the solid. I do not need to put the aqueous. But you will need to put any concentrations in molarity and any pressures in atmospheres, just like when we did KEQ. So all ions are going to be given in molarity. All gases in atmospheres. All right. All right, again, right. So you're starting with the anode terminal, the solid that you're connecting your alligator clip to. Again, a single slash. I usually write my slash with a slant, not straight up and down. That is indicating a phase boundary because the Zn plus 2 is in the liquid phase. They're saying vertical. All right, whatever. I always had mine slanted. All right, now if you have a half reaction that is not a metal, you have a H plus going to H2 gas. Again, you have to start with a metal and you have to end with a metal. If there is not a metal, if there's no metal in the half reaction, you're going to use platinum. So platinum is an inert metal, excellent electrode. It's not going to change the reaction, but it will let the electrons flow from your anode to your cathode. So when there's no metal in your half reaction, always use platinum. Sometimes you can use something else. Sometimes you can't. You can always use platinum. All right, so again, here's a half reaction. You have aqueous, you have gas, there's no metal. Now you're going to use platinum as the electrode. All right, and so the way that they had it written here, they have it written as a reduction, H plus going to H0. Note in your cell notation, you don't have to balance your reaction. This is not a balanced reaction. If you put 2H plus here, I will not count it wrong. It is not required, but it's not wrong if you do it. At least if it is wrong, I'm not going to take off for it. And again, there's no concentration given. If there's no concentration given, it is the standard 1 molar. I would put the 1 molar there because if it has a molarity that's not 1 molar, then it has to be there. Same with your gas here, hydrogen gas, it should have 1 atmosphere. All right, so all of your concentrations, all of your ions that have a concentration, I always would put 1 molar there so that when it is 0.1 or 0.3 or whatever, that I don't forget to put it there. If you are given a concentration that's not 1 molar and you don't put it in, you have the wrong cell notation. So even when they are 1 molar and 1 atmosphere, I would put it in there. All right, so here would be a question on the test. Write the cell reaction for the voltaic cells. All right, so we just know that this is going to generate a electricity. It's a spontaneous reaction, and that means delta G is negative. All right, so we have TL solid going to TL plus. All right, and so that's what that is telling us. And so again, here is always, it starts with the anode. And it always ends with cathode. All right, and so we know that this is our oxidation half reaction. First one always is the anode, the oxidation half reaction. And then the second one is the reduction half reaction, where we have our SN plus 2, our 10 plus 2, going to SN solid. All right, and so to balance this, we need 1 electron. To balance this, we need 2 electrons. So we'd have to multiply this through by 2 so that 2 electrons lost equal the 2 electrons gained, and so that they are subtracted from both sides and they cancel each other out. All right, and so then you bring it down. 2TL solid plus SN plus 2 yields 2TL plus and SN solid. So that is your overall reaction. All right, for the zinc, the next one you have part B, your zinc going to zinc plus 2 plus 2 electrons. This is your oxidation half reaction. That is your anode. And then the next one is, note here that you have Fe plus 3 going to Fe plus 2. There's not a phase change because they're both in the liquid state. And so here there's no metal in this half reaction of going from Fe plus 3 and being reduced down to Fe plus 2. There's no metal. Again, when there's no metal, you have to have a solid metal electrode to connect your alligator clips to. When there is not a metal in your half reaction, you put in platinum. All right, and so we needed our 1 electron for our Fe plus 3 to go to Fe plus 2. So again, when you add it up, the electrons gained have to equal electrons lost. We lost 2, we need to gain 2. So multiply this through by 2. And then your 2 electrons are subtracted from both sides, and you have your zinc solid metal plus 2 Fe plus 3s, yielding 2 Fe plus 2s and a zinc plus 2. All right, so you should be able to do both ways. You should be able to go from a cell notation to a reaction. You should also be able to go from a reaction to a cell notation. All right, so here is where they are finally putting in the concentrations. So again, if it doesn't give you any concentrations, all concentrations for your ions are 1 molar. Every time you have an ion, it's 1 molar. And note here, they're not balancing the reaction because this would be 2H plus going to H2. And then again, if you have a gas, hydrogen gas, you don't put it in molarity. Gases are put in atmospheres. Your ions in solution are always put in molarity. Again, your hydrogen does not have a metal, and so again, you have to end with a metal to hook your alligator clip to. The zinc does have a metal. You can hook it right to your zinc solid. Of course, it always starts with the anode, and that is your oxidation. And then you have your salt bridge. And then you have your cathode, and that is your reduction half reaction. All right, again, if you have this single line, mine's normally slanted, but they're putting them straight up and down, fine. This means you have a phase change. You have a solid, you have a liquid. Here you have a liquid, aqueous, H plus. Here you have H2, which is a gas, different phase, so you need to have a phase change. Then you have a gas going to the positive metal electrode. Again, you are changing a phase, and so you have your single line. All right, so again, I would always put in my concentrations, because when they are giving you a concentration and you don't put it in, then it's wrong. If they're all ones, then you're fine. But many of these are going to give you a ion that is not a 1 molar, or a gas that's not 1 atmosphere. All right, we will pick up there next time.